Hello, statistical machine learning class. Congrats for reaching to week 12 of the learning journey with us on machine learning. Um, I'm Lexing, I'm back. So it's a pity that I won't join you in person tomorrow at the week 12 lecture, but I thought I will use this recording to speak to you about several things. So by this time of the semester, I hope you have had a distinct feeling that, oh, you have learned a new skill and you can use it to save the day in a way that superhero does. Slightly more seriously. So, what I aim to do in this short recorded review section is first to give uh, another brief recap of the first half of statistical machine learning that we focused on in week 1 to 6. In particular, I would avoid repeats, but I will also do it in a way that take us a step back to discuss what are the variants of models, um, learning algorithms, in the big picture of data and evaluations and things we need to do for machine learning, with a few gestures connecting to what you have learned in the second half of the SML class with Professor Jing Jiang. The second part of this lecture is basically a number of reflections on machine learning beyond models and algorithms. I would say that there is a distinct reason where in the whole SML class, we have focused on exclusively on SML, right? The models and algorithms of statistical machine learning. But this is the end of the semester, and as I've hinted in the beginning of the class, you should always place what we learn in a bigger picture. The reason for this focus is by focusing on technical core, it gives you a solid foundation to think about what is machine learning and what is not machine learning, and what it truly can and cannot do, what are the underlying crucial assumptions. Um, this topic itself has become incredibly big in the last decade or so. And what I cover below, of course, is a selective few topics that happen to come to my mind or intersecting with what I think is important these days. So overall, needless to say, the general sentiment that I'm hoping to impart on you and with myself and my own research group is a strong dose of optimism. Machine learning is incredibly powerful. They are changing our world. There are many opportunities, but also with a strong dose of caution. If misused or not deployed carefully, they can cause irreversible harm at scale very fast. Okay, let's get into it. So for the first half, I suppose I probably don't need to remind you of this cube structure that we spent so much time on during week 1 through 6. In today's recording, I would like to intersect this with what we looked at as basically the picture of how to define and solve machine learning problems in the real world. So if we intersect these, what kind of views do we get? This is not to say that I do not care about or won't hold you accountable for all the details in the Zubin's cube. But if you are after the detailed review of this, we produced this picture in week 6. And I recommend anyone who wants to go review that part of the lecture video. So in that video, we essentially redrew this cube and reviewed all the crucial formulations. So hopefully that will help review individual models. So what we are going to start with is this view of, let me see, right. of what is a model definition. So basically, what are our assumptions? What is our mathematical expression of what's being learned versus learning? Basically, what are the procedures we carry out computationally in order to estimate parameters of the model? This can be fairly confusing for people who are new to machine learning and takes a bit of practice. And I think one semester is not too long to sort of revisit this again with specific instances that we have encountered this semester. So first of all, let's look at a few examples of what are the models and representations of the problem that we looked at in and around the Zubin's cube. Okay, there's no green in this cube. Let me write in green. Um, so the first model that anyone encounters in machine learning is, of course, we're interested in estimate a function that is a linear combination of the input feature, right? Right. In the regression case, y is in the real line. And in our textbook and many other scenarios, we can make this more flexible by saying, oh, we're doing y, w times phi of x, a feature function of x. Right, so this is the model. When we change from a regression to a classification task, our model also changed. So its probability of the label equals to 1 given x and w is sigma times w transpose x. I'm going to omit phi of x just for simplicity. Right, so this is a different model because now it's logistic regression and we're learning classification rather than regressions. And when we move to kernel classification or support vector machines, what we're learning is y equal to the output label equal to the sign of w transpose x, or this is in the original input space, or feature space if x is phi of x, or in what is called the kernel space, sum over I going from 1 to n, alpha I, pi, kernel value of x times x between x. This is the new data, test data, and these are the training data. So in the kernel view, the weights are implicit rather than explicit. And when we're performing a Bayesian, when we're working with a Bayesian model, one of the stereotypical examples is the Gaussian process. What we're asking is essentially probability of a new y given the input x, new x. And then after observing lots of x-y pairs, I going from 1 to n. And when we're being Bayesian, in this particular cube, it means this what I call the strong sense of Bayesian. So basically, in Bayesian, let's say in Bayesian linear regression, what we're interested in is also probability of a new y given x, right? And the set of inputs, so BR. So the training data, we usually call the training data is xi and ti. I goes from 1 to n. So these are the training data. PI. So BLR essentially doing this, but it is doing so in a way that marginalize out all the training well, all the possible weights, right? You do something like this, P of Y weights given X. And this is your Bayesian inference. Whereas in Gaussian regression, the dependency of and explicitly marginalizing out the weights are disappeared. Instead, we assume that this conditional probability assumes a normal distribution of which is the mean is a function of the input and the variance is also a function of the input. And of course, the individual respective expressions depend on all the training data, as you remember from the last page, which we're not going to walk through. So this is pretty much the different models we talked about. As you can see, different model assumptions leads to different expressions. And later on, beyond the Zubin's cube, the simple Zubin's cube, we also talked about, well, in the lingo of making something Bayesian and kernelized and probabilistic or not, we talked about principal component analysis. And in the lab, you have practiced this in a number of ways. You have made this kernel PCA, like how do we express principal components in kernels, and also probabilistic PCA, where how do we express the probability distribution of data given continuous latent variables? Moreover, in the second half of semester, you have looked at neural networks. In fact, last week, the first assignment question about neural networks and how backpropagation works. As you know, you can also make Bayesian neural networks, which is not covered in lecture, but with these knowledge, I'm sure you can essentially transplant your understanding about Bayesian models into neural networks. Moreover, the literature on Bayesian neural network is huge, and you can think of a number of example ways, right? So you can just say, and the terminology are not very consistent. Some of neural networks was focused on estimating essentially uncertainty in the output, which is not strictly Bayesian in the sense of it is right. So it doesn't have uncertainty in the weights. It doesn't have prior on weights. Another popular variant, which is computationally somewhat efficient, so it's basically prior on last layer weights. And of course, you can have full Bayesian treatment, basically full prior on all of the weights across all layers. Given how computationally expensive our some of the Bayesian treatments in means, you can imagine that doing full Bayesian network on a large scale neural net is going to be hard, computationally hard. You can also kernelize or kernelize Bayesian neural network. There's literature on deep Gaussian process that goes in this direction, right? Just to show you the same concept or lead to different model variants that will be useful both in practice and also in research. So now let's move to the next page. We're going to preserve the discussion of probabilistic PCA. Copy. Wow. Wow. Okay. Um, so we're gonna keep it there. In the second page, we are going to not look at the models, they are on the previous page, but look at distinct learning and inference and optimization methods that are being used. So I think these few terminologies are somewhat intermingled and sometimes confusing themselves. In terms of SML, or basically the old style, classic machine learning, statistical machine learning, learning is usually, so let's assume our parameters is W, whether it's a tensor, a vector, and so on. So estimating this is usually called learning. And inference in the probabilistic literature usually refers to essentially estimate a new y given an x and w, or distribution of w, posterior distribution, and so on. And the optimization, I would say, borrowing from the operations research and numerical optimization literature, it to me it still strictly means that we're minimizing a function f of x over the parameter space x, subject to a set of constraints, right? So a of x, a set of functions that are less or equal to 0, right? So this translating into the machine learning setting is after we have decided the model and the way we're going to inference, then carry out the numerical optimization. So this is more essentially a numerical optimization view of both learning and inference. So in a lot of models we talk about, such as linear regression, once we know W, it seems that obtaining X or what estimates of Y given X and W is trivial, but in sometimes it is non-trivial, and performing inference itself needs optimization procedures. Okay, so what are the some examples of learning and inference that we have looked at? Of course, we have looked at things that have analytical solutions, such as in linear regression, the optimal weight is given by phi transpose phi plus alpha I d dimensions, or in m dimensions, inverse times phi of t. It's a vector. Right, so these are input features. And this is both a regularization parameter and also we can think of this as prior variance of the wave vector. That's a basic view. They are mathematically equivalent. Yeah, you can have this, you can have the kernelized version. Right, so see 2 pages ago, I'm not gonna write it out now, but you get the idea. So with our footing on this solid foundation, we quickly moved on to things that cannot be solved in closed form. And there are many models like that. Most expressive models that are widely used today are of this class. For example, even in logistic regression or so-called one-layer neural network. So we can write out the So it's also worth asking. So we also, right, so let's also review this terminology, right? So maximum likelihood estimate refers to maximizing the data likelihood given the model, right? And the likelihood function is this strange or object where the function variables are the parameters to be learned, and the input is our training data. These are the constants, right? And then maximum a priori, you can think of it as, well, maximize probability of xi ti base rule. It's better off writing what I said. Basically, maximum likelihood does this, maximize data likelihood given weights. We go from here to maximize the joint between the data likelihood and weights. The difference of this is the addition of the prior term P of W, right? So once we decide which version of likelihood we're optimizing, we convert this to a loss function or log likelihood function. And in more often than not, in machine learning, we do a negative log likelihood. Let me just write down negative 2, because this one we can essentially map to the terminology above. We minimize this negative log likelihood function in order to get our weights. That is, which is the case in logistic regression. So in logistic regression, despite there is no analytical solutions, what this leads to is a convex optimization program. And we, so this, a few notions in elementary optimization are very important in machine learning. So whether a function is convex, meaning ball-shaped in low dimensions, determines whether or not there is a unique global minimum that we're going to, that that exists and can be easily found, right? So the nice thing about logistic regression is it is convex, and if we perform gradient descent under nice conditions, we're gonna get the solution, the one solution. And when we talked about kernel classification, such as support vector machines, it's also convex. Furthermore, it is a subset of the convex program that's called quadratic program. That means SVM also has a unique global solution. And because it's a quadratic program, so think of this as essentially generalizations of quadratic functions that we see in high school algebra. There are many specialized solvers that are designed for supervector machine kind of quadratic programs, that so that it can be solved faster. This is a body of literature that has not had much attention recently, but may have a revival, who knows, in a number of few years, and it can be useful in different places. So beyond optimization, we also looked at approximations, let's say approximations in learning and inference. So here's we looked at Laplace approximation. Basically, it amounts to fitting a Gaussian around the mode of the likelihood function. And we have applied it to both Bayesian logistic regression and also GP classification. What we haven't really looked at was variational inference, which I hope that maybe we will have room for them, make some room for them in the next year's SML class. And there are many different methods in approximation inference literature, which is in the Bishop book that we didn't have room to cover, such as expectation, propagation, power EP, and so on. Moreover, if we think of optimization methods as essentially doing descent, let's say we do this on the multidimensional landscape, we have introduced another set of methods, right? So I will put direct in quotes, right? If you think about optimization as basically going downhill or uphill in optimization landscape, we introduced EM algorithm, or Professor Jinjiang introduced them in the second half of the semester. That basically does what's called EM, is a way of doing coordinate descent ascent. Meaning what EM does is, first of all, sometimes it changes the optimization problem, right? So a little more detail here. So in EM, we first write complete data likelihood. So take the case of PCA and probabilistic PCA. In probabilistic PCA, we have two options. One is, right, so we have data is X and latent dimensions is Z, right? And the approximation goes roughly X is some projection matrix times Z plus some noise, right? So in PCA, we write out essentially probability for X. And then in the EM version of this algorithm, probability PCA, we write out probability of X and Z, the joint probability of X and Z, and then tackle it from there. So this is pretty similar to the Gaussian mixture models that you have worked through in EM algorithms. And in the optimization lens, you can think of EM as doing coordinate descent, right? So some of these dimensions might be X, some of them might be actually X is given, right? Some of this dimension might be estimating W or the mixture components, and then some of the steps are estimating Z, basically updating what the latent component is. So hopefully that is a somewhat useful way to look at, say, PCA mixture model and some of the topics across the two half of the semester that you went through. Another thing I wanted to mention, I'm running out of space a little bit on this page, is I'm just gonna sneakily make some space and write in a different color. Hopefully you can see it. Is that so in terms of computational complexity, what we have done in the first half of the lecture is at most cubic, right, in the elementary components. So it's either cubic in the number of data points or number of dimensions. Because of the matrix inverse. that is involved. So I feel like for machine learners, it's very useful to know or have strong intuitions about how much some computation is going to cost, from matrix multiplication, different matrix manipulations, including the inverse, and other operations such as computing determinant, scholastic factorization that we talked about. But in the grand scheme of things, so these are almost all of the computational requirement we talk about, including training deep neural network, are low order polynomial algorithms. So if you take the optimization class next semester and when it goes to the second half, discrete optimization, or AI planning, some of it you are taking the AI class in this concurrently this semester. So discrete optimization, AI planning, a lot of them are NP hard questions or NP complete questions that are much harder to solve. And it is not readily amenable to the mostly continuous optimization methods we cover in this particular class. So hopefully that piques your interest to learn a bit more as well. And there are different complexity classes that we have not even covered. So go back to foundation of comp and seek some inspirations. So the intersection between machine learning and these computationally very hard problems are also exciting. All right. So that concludes my essentially one step back review of what are the models and representations and all what are the learning inference optimization methods and what does it mean computationally. I'm going to switch gears and swap to this high level and hope you're thinking with me kind of mode. So I've picked a few examples that seem interesting recently, or not so recently, and I will just selectively comment about one way of thinking about them. You might find them useful. There's of course a vast amount of other examples that are worth your dose of critical thinking. Just look at newsfeed about AI every day, and there are plenty of examples. So, okay, here, let's start again from an XKCD example. Okay, so suppose, actually this is satirical, but also surreal in that it is actually deployed in many different companies these days. So when you apply for a job, it's very likely it is an AI, a computer that's reading your resume, right? And what the goal of this kind of problem is basically trying to predict someone's future job performance as a function of their resume. So of course there's many issues so what are the issues for this, right? Of course you can raise many concerns from the modeling and algorithm perspective, as we were illustrating, right? So is this a linear model? What do you mean weights, right? And then right, what algorithm are you using to estimate these weights? Are the weights we get back exact estimates or junk? But let's not talk about that, right? So I would like to start by criticizing the setup, right? So the setup, going back to the big picture we had before, right? So from the real world, we take some observations and call them data. what is data is highly controversial and it has very high stakes. In this particular case, what you write and what you don't write in a resume is data, right? Um, but is this a good setup, right? So written records is, yeah, a written resume is not equal to someone's data, right? Yeah, a person's professional profile. In fact, it's so controversial about what constitutes data. And of course, acknowledging that we cannot capture everything about someone or about something as data, then what is data is essentially a trade-off decision, right? So you can say if you can afford to get someone's reference letters, that will enrich the data. If you can afford to interview them, then that will enrich the data, but they are still data. You can also question the validity and trustworthiness of this data. So basically, there is no perfect data. We are all making trade-offs, and especially when these trade-offs are about other humans or groups of humans, the trade-off becomes very important. Another thing is this objective, right? This is this goal of um, estimation, future job performance, and simplicity speaking, it should not be a number, right? I know in a lot of companies, the performance review results being actually one of three numbers, right? Exceptional, satisfactory, and not very good. That is not the way to evaluate a human being. And of course, a good job performance is very much multidimensional. How well do they work alone? How well do they work in teams? How well are their technical skills? How well their communication skills? And these are essentially human to human tasks, right? If you hire someone on the job, then they should have a mentor or supervisor who help them navigate the complexity of the job and help everybody to be their best in a job, in an ideal world. Okay, perhaps enough said about this toy example. The second example is this particular paper have spread around Reddit and also my friend's circle recently. It is a paper that essentially says, right, AI weather forecast does not outperform old-style physics-based numerical simulation models. I would say one, it is well known in the climate modeling community that in order to forecast global climate, it's obvious that from long-term forecasts, whatever the model has had as training data, it is not similar to the testing data anymore due to all of our human activities and all the CO2 emissions we accumulated in the last 200 years. This is sad, but this is essentially a painfully obvious point to us machine learners that if we would like to deploy a machine learning model, a lot of times there is a drift in training and between training and test data, and the models break. So back to this picture about we talked about the data component, we talked about models and learning. In EM, we talked about different ways of choosing objective. What was not in this picture, but I think it's worth us talking about it for another 3 minutes, is basically the question of how well uh, do we do? As students in a university, you're probably used to anticipate being tested on exams. So of course, AI models have been relying heavily on exams as well. And these exams are benchmarks, right? Um, this particular crowd, or we haven't put much emphasis on benchmarks in evaluation. And I think the last lecture might be an opportunity for us to spend a few minutes to think about it, right? So on the left were two famous benchmarks that I would think you have seen. So the first one is MNIST digits. So this is from the 1980s until now. So much so that I'm sure at least one tutorial in this class are still using MNIST digits because they feel the early growth of the machine learning as a field. Actually, Yang LeCun designed or is part of the team that designed convolutional neural networks on MNIST digits. Um, yeah, and he's still the test ground for many new machine learning ideas. If you have read papers from the last 10 years, lots of them were validated on MNIST digits too. The second one is ImageNet, order of a 10 million labeled images from the internet. This was done in around 2007 to 2009 by Feifei Li and her then student Jia Deng. Both of them are professors now, and a bunch of other people. This allowed AlexNet or deep learning to demonstrate its power in learning image recognition. Right. And fast forward 15 years. So this is roughly today. If you go to Hugging Face, you'll see, oh, here's the big benchmark collection. Each of them are amalgamation of many big benchmarks. And then this is a survey paper in about 2025, listing main benchmarks. As you can see, many organizations have proposed their own benchmark on all kinds of things. It is very costly to create benchmarks. But then with the essentially garden variety of big benchmarks, the community has been quite aware of, hey, what are these benchmarks actually doing? So if the benchmarks are exams, then are passing these benchmarks equivalent to passing exams? In a way, it is. You can think of benchmarks are exams, but what are the exams? Measuring is less clear. So in comes the notion of what's called construct validity, right? So what are the benchmarks actually evaluating? A lot of benchmarks are not being clear about this. Furthermore, a lot of benchmarks themselves are AI generated, have many quality issues. So if you do use some of them, be careful. And then are the skills being tested actually the skills we think they are being tested? The answer is also no. So it comes a time where evaluation and benchmarks needs a rethink. I'm listing below two papers that I recently found very helpful in this topic, but let this serve as a warning to you that if you develop a machine learning algorithm for a particular purpose, don't blindly trust the benchmarks. Look carefully at your results, look at the instances, and really try and understand whether the model is delivering what you want it to do. Okay, another thing I feel like worth emphasizing and re-emphasize, we saw this slide in the very first intro lecture. Basically, the machine learning algorithm code is this piece in the middle in a deployed system. All the other code around it are essentially configurations, constructing and verifying data. And then if you're running a large machine learning system, you need to do resource management in a way that intersects with computer systems and how fundamentally how computers should work. What are the safety and resilience constraints that you wanted, properties you wanted to have? Otherwise, your fancy machine learning algorithm will just crash, right? And then you also need to monitor, right? So the training data and test data mismatch is one good issue that we monitor, but you also need to monitor many other things. For example, disk failures in a large system. Just last week, some of us had a meeting with the National Supercomputer um, Center, and someone delivered a box to the front desk as we were arriving. And the director explained that every day there's a whole bunch of disks failing. So therefore they get a constant delivery of hard drives and need to replace them. And how to do so in a data safe way is very much also a computer systems challenge. So most of you are computer science students where you're well positioned to tackle not just the algorithm foundation. Now, with a solid understanding of the algorithm foundation, you're better positioned to essentially make contributions to all these other different parts of the machine learning system. Moreover, machine learning systems that are what we call socio-technical because they position themselves essentially they're built by people. I would say lots of people and collaborating together, how to get the people to work together is so that the whole system is maintainable is a challenge. And then they are used by and also affects lots of people, right? So thinking about the complexity of machine learning in the whole ecosystem is important, needless to say. Um, I think this year or the last few years, you cannot go without mentioning like teach a machine learning class without mentioning AI safety. Well, it is essentially machine learning deployed the safety of deployed machine learning systems. But now that the word AI has essentially bled together with machine learning, let's just call it AI safety. Um, One painful analogy that I feel was the similarity between this and nuclear weapons. So if you haven't watched, I recommend watching this 2023 film talking about Oppenheimer. And as you watch it, pretend that we're not like mentally substitute nuclear bombs and AI, and you will find the analogy painfully relevant. And people about nuclear bombs, they were not anticipating the many people did not see this coming, right? So just a few years prior to the instantiation of a nuclear bomb, scientists have written articles saying, hey, it can't happen. Luckily for nuclear bombs, it is still a war safety threat, right? Um, but it seems that the humanities have made a concerted effort to contain the threat. It may be fair to say that worrying about AI doing harm to each individual person is a bigger current worry than those by nuclear bombs. But the difference of AI and nuclear bombs is that, let's say, nuclear weapon, right, it is controlled by a few people in the world and then affects many. And with AI, it is, again, the development is controlled by a few corporations, but the use is by many ordinary people, and it has the ability to do massive harm. It can harm many. This is super concerning. So on this topic, one particular resource that I recently found very helpful is this particular blog post and conference keynote talk, right? So this is conference keynote talk, meaning it's well prepared at the Large Language Model Conference on Large Language Models 2025 by Nicholas Carlini, who is a well-known AI safety researcher working for Anthropic. So needless to say, with great power comes great responsibility. You now are equipped with some of the powers knowing how the underlying machine learning works, right? I highly recommend you have a read or have a watch. This particular talk offers a catalog of concerns on AI. What are the different harms AI can cause, are already causing? There are many. And hopefully it gives you a few thinking points about what one could do about it, what a society could do about it, and what you could do about it. So these are in the hands of next generation AI practitioners and researchers, basically you. With this said, I'm borrowing a cartoon to conclude this review section. If we say elementary and secondary school give, and also most of the university foundational content gives us a solid and well-rounded grounding of our knowledge, we hope that a 4,000 level course such as statistical machine learning basically gives you a specialization and a fair grounding to understand the boundary of human knowledge, right? So let's imagine this. There is a geometric shape of the boundary of human knowledge. This is to say, the more we know, the more we know we don't know. Meaning when we're at the edge, we're in touch with lots of unknowns. So you're equipped with the foundations to explore the unknown and change the world. I wish everyone good luck and enjoy your journey. So as we prepare for the end of the semester, I will monitor ed questions with the teaching team. And good luck to everyone. See you later. Bye-bye.